Okay, so hello everyone. We are very happy to have Keerthi Madapusi from Boston College. He's going to talk about a new approach to p-Hecke correspondence and Rapoport-Zinkspaces. Thank you very much.
Yeah, well, thank you very much for the invitation. It's very nice to be here, if only virtually. Um, and it's like people from all across the world, it seems. Uh, it's very grateful. So yeah, so I want to talk about essentially the notion of an isogeny, or more specifically, the notion of a p-isogeny. Uh, and uh, the essential idea is to try to understand uh, p-adic properties, p-adic geometric properties uh, of Hecke correspondences. So that's um, so just as I'm uh, the classic Hecke correspondence kind of shows up in the following way, where you take the upper half plane, let's say modeled out by SL to Z. So this is the classical level one modular curve. Uh, and then what you do is you have this group gamma naught of, let's say, P. So remember, gamma naught of P is a group of matrices uh, in here where, let's say, C is congruent to 0 mod P. And there are two maps. So there's one map that just comes from the um, embedding of, so there are two maps from here to SL2Z. One is just the embedding, the tautological one. The other one is given by conjugation. Some might mess this up, so okay, I apologize. So if I conjugate by this matrix, or maybe the other way around, that gives me another map to SL2Z. And when you use these maps, you get these two projections from H mod gamma naught of P to H mod SL2Z. And this is sort of the classical Hecke correspondence. It's a geometric one. And once you have it, um, you can do various things with it. You can use it to study uh, its action on étale cohomology. So there's anytime you have a correspondence, you have a kind of you can pull things back along this map, and you can push things forward along this map, or the other way around, uh, if in any reasonable cohomology theory. So um, uh, so this is uh, one second, sorry. Um, so okay, so in any reasonable cohomology theory, you can use this geometric correspondence to get some kind of operator from the cohomology here to itself. So it's an endomorphism of this guy, and this is the operator TP. So this is it's obtained from this geometric guy. Uh, sorry, one second. Sorry, that was a little baby emergency, a minor one. Okay, so uh, the uh, the thing that's nice about this correspondence and makes it kind of manageable is that these maps are actually finite. finite étale in this setting. And so this push-pull kind of thing that you're trying to do usually worked quite well in any cohomology theory. Like, so this could be singular, étale, coherent, with values in some appropriate coherent sheaf. And for all of these, this kind of thing works quite well, and you get the various kinds of Hecke operators acting on the spaces of modular forms. Basically, this is kind of the story there. So a lot of the times, when you want to understand the arithmetic of these operators, you find yourself wanting to kind of, first of all, define these operators over number fields. You have the theory of canonical models for modular curves, or more generally Shimura varieties. And so to study the arithmetic properties, we need, so basically, models for these operators, so these correspondences over number fields. And this is the theory of canonical models. But we also need, to really study what's happening, we need to understand the mod P behavior of these correspondences. In other words, we want to understand what's happening with respect to something like Frobenius mod P. And so, well, this P need not be the same P as this, but that's when it's geometrically interesting. Okay, so we also want models, in fact, over rings of integers. That we can study sort of mod various primes. So, so what we have here is a sort of the first basic instance of a p-Hecke correspondence. And studying its behavior mod P leads to things like the classical Shimura-Taniyama formula, or the Eichler-Shimura formula, sorry, for the eigenvalues of TP and this relationship with Frobenius eigenvalues. And so that's kind of part of the story. So the way you get these models usually is via a moduli interpretation. So again, you have H mod SL2Z, you can interpret this as the curve y of 1. It's the C points of the modular curve of level 1. And this is the set of C points of the modular curve of level gamma naught of P. So again, remember, so the way this works is this is a moduli of elliptic curves. And this is the moduli of what are called, well, okay, let me just put it this way, cyclic p isogenies. This is a little redundant, but still, cyclic p isogenies, E1. So this is moduli of elliptic curves E. Let's say E1. This is moduli of elliptic curves E2. And this is the moduli of cyclic isogenies alpha from E1 to E2 of degree P. So this hat diagram that we have here, which is sort of in the realm of locally symmetric spaces or even open Riemann surfaces, has sort of an algebraic interpretation in terms of elliptic curves. And the projection maps are just projecting onto the source of the isogeny and the target of the isogeny. And so this is something that falls out of the classical interpretation of H mod SL2Z as a moduli space of elliptic curves. But you see, this model makes sense over Z, actually. And in this setting, you get this, both 1 and 2 kind of are being taken care of by this correspondence. And in the classical sort of, well, this is already known, but if you kind of look at Katz-Mazur, then you'll see that this is actually still a diagram of, so this is all these maps are finite flat maps of regular, stacks. You can just think of them as schemes, the Deligne-Mumford stacks. And so you can still push through this kind of push-pull picture for a lot of cohomology theories in this setting. So you can pull back here, and then you can push forward here. Because in most of these cohomological correspondence built out of these kind of hat diagrams, they allow for finite flat maps in a very clean fashion. Okay, so this is the situation for elliptic curves and the modular elliptic curves, and things are quite nice. You can also do this. We can replace P by a power of P. You can replace P by really any integer with the same definition. And things work quite nicely, and you get a whole theory of geometric Hecke operators, Hecke correspondences, that give you sort of the geometric underpinning for the action of the Hecke algebra on the cohomology of the modular curve. Any questions? Okay, so what we like to do is to push this through in higher dimensions. And there's one kind of difficulty that shows up. So there are several kind of issues that I want to point out about sort of the way the existing story of Hecke correspondences works. So what about higher dimensions? By this, I mean, you can interpret this in several ways. So one natural way to interpret this is if you replace the moduli of elliptic curves with the moduli of, let's say, polarized abelian varieties, which is, so if I take the moduli of polarized abelian varieties, let's say, sorry, let me take AG of principally polarized of dimension G, then you can play a similar game, except that it's the notion, there's this word cyclic that I used here. This doesn't really make very much sense in higher dimensions. It's a very particular kind of phenomenon that you know kind of is only really sensible in this what you can call a rank 1 situation. But you can still make sense of isogenies between abelian varieties. So let me kind of just define something like this. This is going to be the moduli of principally polarized of isogenies of degree P to the R isogenies, A1 to A2, of dimension G, principally polarized AVs. And there's other things you can add. That's because there's this polarization in this picture. You can kind of ask for some relationship with that polarization. But anyway, we can just kind of take this. So unlike in the situation of G equals 1, which is the case of the elliptic curve, this is never finite. So for G greater than 1, the source and target maps are are never finite, even though, so they're generically finite. When you restrict to what's called the ordinary locus, you do get something finite. But when you go over something like the supersingular locus, then you tend to get large families of isogenies that are sort of higher dimensional families. And in this case, you see that then it becomes a little bit less clear how you should go about trying to do this push-pull operation, in especially when it comes to something like coherent cohomology, but also for other things. So, but you can still do it. The bigger issue in for me, at least, is that even if you do this, at the end of the day, what one likes, what one would want to get, actually, when you do this kind of procedure, so this gives an action of the, let's say, or this underlies, so this TP, well, okay, it's not enough, but anyways, so this gives an action of what you can call the spherical Hecke algebra on the cohomology of this guy. So this is the Hecke algebra kind of generated by cosets of SL2, double cosets of SL2ZP inside of SL2QP. And that, or okay, let's just say that. I think it's better to work with GL2 actually for this, but still. So this is that kind of algebra. It's a commutative algebra. It's actually just a polynomial algebra in one variable in this case. And it acts on this guy. And it's easy to see because essentially this guy is more or less is the generator in this setting. But when you try to do this higher dimensional situation, even if you define some kind of correspondence, so even if one defines a correspondence, and via this procedure, it's not clear what it has to do with the spherical Hecke algebra. And usually the way you kind of get around this issue, I mean, there are various ways to do it, but one way to do it is you use some action of correspondences built in this modulate theoretic way, and then over the generic fiber, you can show using basically the technique of uniformization that you see over here that you have an action of spherical Hecke algebra, and then you use some kind of density to conclude that you have an action of the spherical Hecke algebra integrally as well. So by what I mean by this is that, so if for example, the kind of group that's relevant to this situation is something, so like the Hecke algebra of GSP2G. And this Hecke algebra by the Cartan decomposition has generators indexed by sort of the characteristic functions of co-characters of the standard maximal torus of GSP2G. And you can ask, like, what is the action of this element? So so in the case of the elliptic curve, modular curve, this TP essentially is telling you the action of the coset of, well, again, there's a little okay, I'm kind of slightly lying here, but okay, it's telling you so the action of a coset like, so really the GL2 is what I should be using here, or PGL2, of this kind of guy. Uh, so, uh, so there are ways of getting around this. So what you can do is you can do something like this when lambda is what's called minuscule, which is the case of the TP in the modular curve case. You can more or less access it by looking at AG of P instead of AG of P to the R. And then you can kind of try to build up the other correspondences by kind of taking products and so on and so forth. But it's kind of ad hoc. And it's not the right thing to do because it is so ad hoc. Uh, so, so what I want to explain is like a less ad hoc way that actually gives you a natural action of something like the Spherical-Hecke algebra, or that should give you the action of something like the Spherical-Hecke algebra. But it involves some new developments in p-adic cohomology theory and p-adic realizations. So, so let me just kind of very quickly give. I mean, I'm just kind of a very impressionistic overview of sort of the background behind that. So this is the story of what. So this is a purely local story. So it is known, for example, that already here, when you want to give isogenies between abelian varieties, it's more or less equivalent to giving isogenies between their corresponding p-divisible groups when you're talking about p-power isogenies. And so at least for the definition of isogenies in this context, really all you really care about in this local context is isogenies from p-divisible groups. And so that's kind of what we will try to access in a more systematic way. And so here's the sort of the local approach to isogenies, or p-isogenies in particular. And this uses sort of a new kind of object, which we call a. So the data that we need for this, the data that goes into kind of defining these objects that you see over here, the modular curve or the principally polarized modular principally polarized abelian varieties. So these are all examples of what are called Shimura varieties, and Shimura varieties are associated with group theoretic data, and they start off life as symmetric spaces like H mod SL2Z, and then kind of, miraculously have models over the number fields and in fact over rings of integers. And it's in this context that we'd like to do something like this. And the local kind of data that Shimura datum gives you is something like this. So what we're going to look at is I'm going to take the data of a G and a mu, where G is, let's just to fix ideas, it's going to be a reductive group over ZP. And mu is going to be a co-character defined over a, so where O over ZP is an unramified ring of integers. And in this setting, you can define these stacks. Which are sort of, okay, I'm just going to write some stuff down, and I'll slowly kind of unwind what's happening here. So here, these guys here is a smooth, zero-dimensional, formal Artin stack over spoof O. So this is the formal spectrum of O with the p-adic topology. And this BTG mu infinity is the inverse limit of all these under smooth transition maps. So this is just some notation that I put on this page. But what these stacks are, I'm just going to tell you something about what they represent, what they are in sort of in an impressionistic way, and then give the definition a bit later. So these stacks are associated functorially with this data. I forgot about an important condition. I need mu to be minuscule, i.e., the action of mu on the Lie algebra of G with the adjoint action has weights -1, 0, 1. So this is a condition under which this is the kind of a local version of the condition that gives you Shimura varieties. We're kind of carrying that along. Okay, so these stacks are associated functorially with this data. That's one thing. The second thing is that when G mu is equal to GLH mu D, where mu D is the cocactor represented in this way, in the standard format, there's a canonical isomorphism to the stack of truncated.
Maybe one should be M instead of N. You have GLN and BTN. Maybe you want to change.
Oh, this is an H.
Sorry.
Yeah, this is GLH. Yeah, sorry. Yeah, maybe I'll write it like this. I don't know if that made it any clearer. Okay, so this is truncated p-divisible groups of height h and dimension d. So I mean, an n truncated p-divisible group. So in other words, these are objects. They're also called truncated Barsati-Tate groups. This is a notation. That's why we have this BT here. It's probably not great notation, to be honest, but this was a notation used by Drinfeld, and so we've kind of carried this along. And so the key point is that these are kind of group theoretically defined objects that in these special cases recover p-divisible groups or stacks of p-divisible groups. And so there's a long history of objects like this. By the way, I see Oliver Bultel is here, and he, along with Papas, constructed versions of these objects using Witt vector displays, but they have like some technical issues that are resolved by so how are these objects defined? So they use this like new machinery due to Butt and Lurie and Drinfeld of these sort of what seem to be like very fundamental objects So the construction this uses these stacks, the cohomological stacks of Drinfeld and Butt-Lurie. And so I'm not going to say anything about these stacks, really, to be honest. I'll just tell you sort of their name. So the main stack that I'm concerned with is the following. So there's an assignment for any p-adically complete ring, a stack that's called its syntamification. What is it? Well, it's more or less a stack built out of. So when, let's say R is an FP algebra, and let's say even is like an LCI FP algebra, then R, the syntamification is built out of and is determined by and determines the crystalline cohomology of R, along with its Frobenius and what's called its Nygaard filtration. So, I mean, this is an object that kind of, at least in the LCI setting, could have been defined many years ago by Berthelot and Ogus, but it's just I think the idea of viewing these things as being somehow kind of manifested in a geometric stack is probably originally due to Drinfeld. He did this for objects, just for the crystalline cohomology without Frobenius or its Nygaard filtration, but then you kind of push it a little bit further, and you get this object. So I'm not going to say anything about what this stack is, but what I can tell you is that this stack is sort of the recipient of, as I said, the crystalline cohomology of not itself, but also a crystalline cohomology of schemes living over R. And in particular, if you know a crystalline cohomology, or in this case, actually, if I want to do it for any R, then I have to work with prismatic cohomology. But one thing about it is that crystalline cohomology or prismatic cohomology knows about de Rham cohomology, and it knows about the Hodge filtration on de Rham cohomology. And in particular, it knows about what's called the Hodge cohomology, which is the associated graded for the Hodge filtration on de Rham cohomology. And a way of stackily encoding that is that there is a map from BGM to the syntamification. So this is like what's called a Hodge point. So, okay, this is something. But what you can do with this is the following. You can define BTG. Okay. So BTG mu n of R is going to be the groupoid of G torsors over the syntamification. So Q over R sin. So by this, so G torsors in what sense? This is, so R sin is a nice enough stack that you can make sense of something like the flat topology on it. And so these are torsors with respect to the flat topology. And the condition that you want is that when you restrict to BGM, this is a boundedness, a bounding condition, and it tells you that this must be isomorphic to what I'll call P mu. And what is P mu? So you see mu is a co-character from GM to G. And so in particular, it gives you a map between their classifying stacks. And this in turn classifies a canonical, a torsor, P mu over BGM times SPIF R for any O algebra R. Anyway, so this is the definition.
Where it
And
ends? Sorry.
sorry, thank you. So you take the stack, which is a stack over, let's say, O or ZP, and then you mod out by P to the N. And so this is now a mod P to the N stack, and you take G torsos over there, and that's this thing. So in particular, you see this equivalence is now telling you that P divisible groups are essentially the same as, or rather, are a fully faithful subcategory of GLH torsors on the symptomification. So let me just write it this way. So when you take the limit over n, you just get torsos over the symptomification. So the symptomification is a p-adic formal stack, which means it's determined by its mod p to the n quotients or base changes. So so the moral of this, at least this, this is very nice because there's various things you want to do with p-divisible groups that you can't because p-divisible groups don't form a tensor category. And for example, even when you want to talk about polarizations, like what does it mean for a p-divisible group, to have a kind of a symplectic structure? You can use this idea of the dual p-divisible group, but when you kind of restrict to p equals 2, then there are some complications to that definition. So these are linear algebraic structures that we want to impose on p-divisible groups, and more that and that's the reason why sort of a lot of the story of p-adic geometry in this context is always kind of done for things what you can call a PEL type or EL type. It's p-divisible groups with additional structure that you can kind of see directly in the category of p-divisible groups. But there are certain structures that you can't, at least not without sort of some restrictions on your input rings and such. But this gives you a very clean way of doing tensor constructions with p-divisible groups. So this is the same as vector bundles of rank H over R sin. And this is a nice tensor category. You can do whatever you want inside of it. So by the way, so all of this is so, as I said, there's some like work along these lines by Bultel and Papas using vector displays, but there are some technical restrictions. So this stuff. So this equivalence here is a sort of a reinterpretation plus some additional stuff of results by Anschutz and Lebras. Who basically proved this for what are called quasi-symptomic rings inputs. But all of this sort of appears in a preprint by my student, Zachary Gardner and me. You can find this on the archive. Okay, so I think I'm running out. Okay, I have like how much time do I have actually?
I think 20 minutes.
20 minutes? Okay, let me speed this up. So so now you see, we want to define a notion of an isogeny. And if you take the perspective that instead of like abelian varieties or p-divisible groups, you should be working with these G bundles or GLH bundles, then you see that you want to rethink how you want to think about isogenies. Because when you talk about isogenies, what is an isogeny, first of all, between, let's say, two abelian varieties or elliptic curves? You can think of it as a pair of maps like this. Uh, whose composition in both directions is some power of p. So this is another way of writing down what an isogeny means. And if you do this for, so this makes sense actually in any kind of additive category. You can make sense of what an isogeny is. It's just a pair of maps whose composition in each direction, like sort of opposing direction maps, whose composition in each direction is a power of p. So in particular, of course, you can make sense of this in the category of vector bundles over anything. And when you do that, you recover the notion of an isogeny via this kind of interpretation. You recover the notion of an isogeny between, or in this case, n truncated groups, but also, or actually, again, let me replace this with, okay, or in between, sort of, okay. So here's the reinterpretation of what's happening here, and which gives you a systematic way of thinking about, what is happening sort of with this other group's G, where you don't necessarily have this interpretation in terms of vector bundles so cleanly. So let me define the following scheme: X HN, or XHR, sorry. And what is this going to be? This is going to be the scheme of matrices so this is actually going to be over, let's say, spec ZP, fixed ideas. So it's going to be a scheme of matrices where products of these two matrices is equal to p to the r times the identity. This is a nice scheme. And in fact, it has a two-sided action of GLH. And the action is given by G1, G2, AB equals G1. Furthermore, when I restrict to the generic fiber, this is actually isomorphic to GLH via the projection. And in fact, it's equivariantly isomorphic to GLH so the GLH acts on itself on both sides by, say, just projecting out of the first core. Okay, so why did I introduce this? So if you have any stack, and suppose I have two vector bundles over it, of rank H, then you can, from them, you can think of them as equivalent to giving two GLH torsors. These are the torsors parametrizing bases for V1 and V2. So anytime, in other words, so when I look at Q1 times Q2, this is a GLH torsor. Okay, so anytime you have a torsor over something, and you have a space with an action by the torsor, you can twist the space by the torsor. And when you do this, what do you get? All right. This is by definition. So by the sort of just unraveling the definition of what this twisting means, all this is the space of maps. In this way. So all this is this space of p to the r, of what you can call isogenies bounded by degree p to the r between v1 and v2. And so here's something you can do. So over bt g mu infinity bt glh mu d bt glh mu d infinity, you have and you take the symptomification of this, you have a universal GLH times GLH torsor, which corresponds under this equivalence this Anschutz-Lebrun type equivalence that I mentioned before. This corresponds to the universal a pair of Petersburg groups. H1, H2 over this stack. And I can do this construction. So I can look at XHR and I can twist it. So this is some space that lives over this symptomification. And it has the feature, this is just a matter of unraveling the definitions once you have those equivalences that I mentioned before. So anytime I have an algebra, and this two Petersburg groups over it, you get, so there's a map from SPIF C to BT GLH mu D times BT infinity GLH mu D that essentially is given by a pair of Petersburg groups. So this is given by H1, H2, and then kind of symptomification of that. Then giving a section lifting this map is equivalent to giving an isogeny from H1 to H2 of degree bounded by p to the r. Again, all of this is just, okay, well, so it's just quite formal once you have the equivalence. So to recap, one way to get isogenies between Petersburg groups, or of interpreting getting isogenies between Petersburg groups is as follows. You have this space, it has a two-sided action of GLH, and generically it's isomorphic to GLH with its natural two-sided action. You use it to twist any pair of torsors. And when you take over this symptomification corresponding to Petersburg groups, and a section of this twist is the same over the symptomification is the same as an isogeny of Petersburg groups with degree bounded by p to the r. All of this makes sense for any group, not just GLH. All you need is to replace XHR for any G mu, but we have to replace XHR with some scheme which has a two-sided action of G and a G times G equivariant isomorphism to the generic fiber. And you can repeat this whole thing. And then you'll get a notion of isogenies. Okay, so I didn't say, so there's a word for the objects that we introduced in our paper. So we call the objects the sections of this guy. This is the stack of what we call G mu apertures. And an aperture is kind of like a window, but smaller. But this is so the anyway. So the idea was that you have these apertures, and then when you introduce some notion of a frame, you can expand the aperture into what you can call a window. I mean, I don't know. This is only makes sense to you if you have looked at sort of the zinc story of displays and windows. But in any case, so what we have here is a notion of an isogeny. So this gives us a notion.
Can I quickly ask a question? Sorry.
Sorry. Yeah,
So
question.
is this X unique?
No. So the whole point is that it is to find the X. So I just, if you have an X with these properties, no, X is far from unique. For example, already in the case of GLH, you have all these different XHRs.
Okay, so for each one of them, you have different notion of isogeny.
Exactly. Yes. So it gives us a notion of isogeny kind of type X. Between G mu apertures. So this is where you need to use a little bit of, so the question is like how to find such X. So if you think about what happened in some sense in this story, you start with a space of matrices. The space of matrices is a monoid scheme with a two-sided action of GLH, and then you kind of restrict sort of the matrices that you allow inside of this monoid, more or less. That's kind of the what's happening with this picture. And it turns out that for any group, there is something called the Weinberg monoid, VG. Not going to say very much about this, but this is a monoid that has a map from G. So it's a monoid scheme. So in particular, because it has a map from G, it has a two-sided action of G times G. And if you fix a maximal torus, or you don't have to do this, but so if T inside of G is a maximal torus, as max, like what you can call a quasi-split torus, then there is a map from VG down to okay, there's a picture like this. And this map here is G times G invariant. So T add is a torus. So it's just, you can think of it as just a bunch of copies of GM, and T bar is add is a toric embedding. It's just actually a bunch of copies of the affine line, indexed by the simple roots of the torus. And one particular feature that this has is that if I fix a dominant character, again, okay. So so that means I've kind of fixed a Borel and such and all that kind of stuff. Then you see you have lambda of P. It's a map from spec QP to T. This actually extends to a map to, sorry, to T add. It extends to a map here. And so here's the definition. I'm going to define VG lambda to be the thing that sits in the following Cartesian diagram. It's just a little kind of, so this is the longest while element. So because this is G times G invariant, this is actually has an action of G times G. And you can show it's generically isomorphic to GQP. It follows from the fact that lambda of P factors through here generically. And so, and here's actually the very, very, at least for me, when I found this, the exciting part of this, which is that if I take VG lambda on any, let's say, the Witt vectors of any perfect field, what I get are exactly what looks like the closed Schubert cell. Inside of here. So I'll kind of stop here, but the point is that if you kind of do this construction that I talked about, where you take X to be VG lambda, then you get a notion of isogeny between G bundles or these G mu apertures. And this notion of isogeny actually perfectly aligns with the action of something like sort of the basis elements of the spherical Hecke algebra. So of course, like instead of getting an action by just this guy, you're getting an action of it and all the cosets that lie under it. But of course, this is like an upper triangular change of basis. So you kind of do get, so this gives an action of some cover of this Hecke algebra. Which is sort of at least has generators indexed by dominant co-characters. And we think this action, I mean, in whatever context in which you're defining it, should descend to an action of Hecke algebra, but this quite requires understanding something more about the situation. So I'll just stop here. Thank you.
Thank you very much. Very nice talk. Are there questions?
I have a question, but in the beginning of the talk, there was I mean, there was some link between E1 and E2. I didn't understand what E1 and E2 are.
Here?
Yes, yes, here.
Oh, I was just saying that you can interpret the two maps from H mod gamma naught of P to H mod SL2Z as I just said, it's the same moduli, except I just denoted one by E1 and the other by E2 to emphasize that one of them is the target of this isogeny and the other is the source of the isogeny.
Okay, thank you.
Any questions?
Well, actually, I have another question. You mentioned in your talk the property of locally complete intersection in the context of symptomification of things. I just have a very elementary question. Could it be possible that affine Linie-Lustig varieties are locally complete intersections? I know that it's a vague question because thus far nobody has ever exhibited a scheme structure on affine linear Lustig varieties. However, it is expected that in many cases they exist. So I think it's perhaps
Yeah, so I know one thing that I had in
person.
the title of the talk was Rapoport-Zinkspaces, and I never talked about Rapoport-Zinkspaces. But the thing is, like, once you have this notion of isogeny, you can define spaces of quasi-isogenies.
Mhm.
And so you can actually get a pretty canonical sort of model over FP for the affine Deligne Lustig variety. Namely, is going to be defined in terms of the sort of the underlying sort of reduced schemes of these spaces of quasi-isogenies. And I think it's possible to show with this and some like Frobenius splitting techniques that these guys are going Macaulay, but I don't.
Okay. So
But I think
it's at
that's
least
the
something.
best. I think that's the best one can hope for in this setting.
Okay.
Sorry, I had a question. Did you you can construct Rapoport-Zinkspaces by this method? Can you also prove that the integral model for these spaces are representable or something about the integral model?
Yeah, because these are all integral. I mean, these are all like formal guys. And yes, so you get the representability. So I mean, the like in my paper with Gardner, like we prove like a very general kind of representability. So if you think about like what this construction is, you have something that lives over like the symptomification of something, and then you're taking sections of it by symptomifications of other things. That's the general sort of format of the kind of object you're getting. And this is kind of like what happens in the characteristic P story. When basically the story of Stukas or whatever's happening in characteristic P is that you have some object and it lives over actually a curve, and then you're taking sections of that curve, and you're using that anyway. So this is the kind of thing that we want, is that you have some object living over symptomification, and I want to take sections of it for symptomifications of other things. And we prove some general results that tell you that when such a thing is representable, and it's representable by a p-adic formal stack or scheme. And so those results tell you that these guys, that the space of isogenies that you construct in this way are representable. So they are sort of integral. I mean, they're kind of, yeah.
Okay, I also have a question. So you said that you needed this X to define the notion of quasi-isogeny or isogeny.
Yes.
And then this would give you Hecke operators.
Yes.
Right. So you are exhibiting one X, like by this Winberg monoid. But
well,
so to what extent does it depend? Yeah.
Well, you get a bunch of different X's, right? That are indexed by these co-characters. So for each co-character, basically what this is telling you is that for each co-character, you get a notion of isogeny that point-wise is somehow kind of an isogeny bounded by lambda. And so you get sort of all these guys acting, and just kind of because these are geometrically defined, you automatically get some kind of algebra acting, and that's why you get this big algebra, and then you have to prove something to see that you actually get an action of something like a Hecke algebra. Of course, this depends on exactly how the action is being manifested in cohomology. But the point is that you have a lot of different isogenies thing that you built here. But maybe your question is how you get a notion of quasi-isogeny. And the point is that, for that to state, the point is that there's a map from VG lambda to VG lambda prime if lambda is bounded by lambda prime under the Bruja order. And so if you have an isogeny of type lambda in this setting, you also get an isogeny of type lambda prime. And as lambda grows in the Bruja ordering, you fill up the space of quasi-isogenies.
And if G is GLN, would you give?
That's a great question. So I don't know what this is when G is GLN, like, or what the actual interpretation is, because the Windberg monoid for GLN is actually kind of hard to understand explicitly for n greater than 3. And so this is a space of isogenies that I don't know exactly how it's related. So when you take the union of all of them, that's you do get the space of quasi-isogenies of reducible groups. But at each finite level, I don't know what that means in terms of reducible groups. Because I don't know what this guy is, like, explicitly in terms of like vector bundles and so on.
But you still get some stratification of this gives you some okay.
Yeah.
And another question, maybe this is technical, but where do you need mu to be minuscule?
To prove, well, you can define all of these things without assuming anything about mu, but you need mu to be minuscule to get representable objects. So
because some deformation, so you need some deformation theory?
Yeah, so what happens is that on the syntonification, you have various canonical line bundles. This is called a Breuer kiss and twist. And the minusculeness of the co-character tells you that when you study the deformation theory of these guys, you only ever see Breuer kiss and twist, the first Breuer kiss and twist, and nothing beyond that. And this is important because the cohomology of the first Breuer kiss and twist is basically the same as the FPPF cohomology of mu p infinity. And so it's representable in particular. Whereas the cohomology of the higher Breuer kiss and twists are known to not be representable. Like they are at least not in any naive sense. And so if you have higher weights appearing, then you'll get these higher Breuer kiss and twists, and then you leave the world of. So I mean, there should be some theory of objects that permits this, but the minuscule condition is mainly needed to get these algebraic objects.
Nice. Okay, thank you very much. Are there other questions? Okay, let's thank Keerthi again. Thank you very much. It was very nice.